This is tutorial number 7. In this tutorial we're going to be discussing the sine wave, wavelength, and the meanings of peak and RMS voltage. We'll also talk about harmonics and a little bit about the oscilloscope. Alternating current is generated by a generator. An AC generator produces AC voltage, and it produces AC voltage because of Faraday's law. Faraday's law is how we generate most of our electricity today, and basically Faraday's law states that if there is relative motion between a conductor and a magnetic field, then a voltage, also known as an EMF, will be induced into the conductor. So if we have a conductor and we have a magnetic field crossing that conductor, we will cause the electrons to bunch up one end. Basically that's how Faraday's law works. I'm going to show you an animated GIF on the radio school website of Faraday's law at work. If you go to the school website and you click on supplementary, and then you go down until you find, looking, here we are. Can't find it. Dear, oh dear. Here we are. Faraday's law. View or download an animation of Faraday's law of induction, animated GIF. Let's click on that. Now I hope you can see that. I'll realise it'll be over to one side of the screen, but you can look at this yourself by going to supplementary on the Radio and Electronics School website. Here we've got a voltmeter that is centre reading, so it's 0 volts in the centre. It goes up to 20 volts on one side and 20 volts on the other. That's called a galvanometer, or a centre reading voltmeter. We've got a coil of wire, and we're moving a permanent magnet in and out of that coil of wire. Notice when the magnet's out, there is 0 volts. When the magnet goes in, the voltage is induced with one polarity. So when it's going in, the voltage swings to the right to 20 volts, and when it goes out, the magnet goes out, the voltage swings in the opposite polarity to 20 volts. That is producing a sine wave of voltage. The current is reversing each half cycle. The magnet going in and all the way back out again is one half cycle. And if we continue to do that, we will have so many cycles per second, and that is the frequency. There are a number of different waveforms we use in radio. By far, the most common one is the sine wave. Here. That's what we were just looking at, created by Faraday's law. So this is the current flowing in one direction, when the magnet goes in perhaps, and this is the current flowing in the opposite direction, when the magnet comes out. This is current one way, this is current the other way. On the horizontal axes we have time moving towards the right, and on the vertical axes we have amplitude. The horizontal axis is called the x-axis, and the vertical axis is called the y-axis. So the vertical axis is showing us the amplitude in volts of the sine wave, and the horizontal axis is showing us how long these cycles take to appear in seconds. Here we've got 2 cycles, 2.5. We've got 1, 2. We've got exactly 2 cycles of a sine wave. On the right hand side is a damped sine wave. That would occur with a tuned circuit, an LC circuit, an inductor and capacitor. If given energy, will produce a sine wave, and if you don't give it any more energy, the sine wave will damp out after several oscillations and stop. The other waveforms that we could encounter in radio is the square wave, rectangular wave. They are also AC. The top is current flowing in one direction, the bottom is current flowing in the opposite direction. Alternating current flows backwards and forth. The electrons don't go anywhere. They simply go backwards and forth. And as the frequency goes up, they actually begin to vibrate and don't have time to travel very far at all. And we have a sawtooth wave for obvious reasons. And again, that is also AC. Above the line is current flowing in one direction, and below the line is current flowing in the opposite direction. Viewing complex waveforms is not easy. You really can't see a waveform on a voltmeter, and so the device we use to display these waveforms is called an oscilloscope. You're looking at a on-screen presentation of an oscilloscope. It's a Java oscilloscope, so it's a fully functioning oscilloscope. And this is the device you use to look at AC waveforms, so you can work out what their peak value and frequency and so forth is. I'm going to give you the URL. You may see it. I'll just drop the screen down a little bit. You can see the URL there of this oscilloscope. If you Google virtual oscilloscope, you'll find it, and you can play with this yourself. You don't have to know an awful lot about oscilloscopes. The main purpose of me showing you this is a basic introduction to oscilloscopes, and also to show you how you can see AC waveforms and analyze them. I'm going to turn the oscilloscope on by clicking the on button, and I now need to feed a signal into the oscilloscope. Let's have a look at this one. There we are. So we've got a sine wave of voltage going into the oscilloscope. This is actually a dual channel oscilloscope. You can display two waveforms at the same time. I'm only going to display one, but I'd like you to have a play with it sometime if you could. So I've got a sine wave of voltage going into the oscilloscope. This axis, the horizontal axis, is time, the vertical axis is amplitude, and we've got the oscilloscope set to about 1 volt per division. So that means that this voltage here is 2 divisions, that's 2 volts. So that's 2 volts peak. So the AC waveform peaks at 2 volts. Then it comes down again. This is the magnet going in, peaks up to 2 volts, falls back to 0. The polarity changes, and with the magnet coming out, we get 2 volts induced in the opposite direction, 2 volts peak here. So that gives us 1 cycle of AC. I can adjust the volts per division and increase the amplitude seen on the screen. I'm not increasing the amplitude of the signal, I'm just increasing the amplitude that you'd see on the screen. And I can also adjust the rate at which the oscilloscope sweeps across the screen, and if I adjust that, I can change how many cycles I see on the screen at the one time. So if I make the electron beam sweep faster across the screen, I can just get 1 complete cycle of AC. Have a play with that yourself. Now, one of the things with alternating current at any frequency, we need a way of comparing it with DC, because DC, if we had 100 volts DC, it would be there all the time. If we have 100 volts peak AC, we don't have 100 volts all the time. We only have 100 volts at these points here, at the peak. So we need a way of comparing AC voltage with DC voltage. We need a way of knowing how much heat or how much work AC voltage will do in comparison to DC voltage. That value is called the RMS value of the sine wave. On screen we've got a sine wave to help you understand the difference between frequency and period, and we also need to discuss the value of an AC sine wave form and its equivalent value compared to DC. Let's have a look at the first diagram. Here we're showing 3 full cycles of AC sine wave. The number of cycles that we get in 1 second is the frequency in hertz, and we're getting 3 cycles per second, so the frequency is 3 hertz. The period is the time taken for 1 cycle. The period is how much time it takes for 1 cycle. In this case, if it takes 1 second for 3 cycles, then the period is 1/3 of a second. The reciprocal of the frequency gives you the period. So if you want to know the period, that is the duration of 1 cycle, the period equals 1 over the frequency. So the frequency in this case is 3 cycles per second. So if we want to know the period in seconds, it's 1 over f, which is 1 over 3, which is 1/3 of a second. If you wanted to know the frequency and you only knew the period, you can find the frequency by getting the reciprocal of the period. The reciprocal of a number is that number divided into 1. So if you know the period and you want to find the frequency, you simply divide the period into 1. If you know the frequency and you want to find the period, you simply divide the frequency into 1. Doing this example again, the frequency is 3 cycles per second, so the period is 1 over 3, or 1/3 of a second. In the bottom diagram, I've shown 1 cycle of sine wave. So the first cycle is the current flowing in one direction. The current or voltage starts from 0, rises to a maximum at 90 degrees, because one complete cycle is 360 degrees. So the first peak is at 90 degrees, and it then drops to 0 at 180 degrees. Then the polarity changes, and just think of the magnet coming out now rather than going in, and the opposite half cycle is produced. The peak value is 1 volt and 1 volt. Both the peaks are 1 volt because it's 2 volts peak to peak, but it's worth remembering that the peaks don't occur at the same time. Because we have time in this axis, time in seconds, the first half cycle is at a different time than the second half cycle, so they don't occur at the one time. So at no time do we ever have 2 volts. We have 1 volt peak during one half cycle and 1 volt peak during the opposite half cycle. The value of a sine wave that gives you the equivalent value of DC is called the RMS value, and that value is around about there, and it's 0.707 of the peak. Now if you remember 7/10, you'll be pretty right. So if the peak value here is 1 volt, then the RMS value, I'll write that in, stands for root mean square. It's a mathematical way of finding out the equivalent value of AC compared to DC. That's called the RMS value, root mean square. So this sine wave would have an RMS value of about 0.7 of a volt. since the peak value is 1 volt. What that means is that this sine wave will produce the same amount of heat or do the same amount of work as 0.7 of a volt DC. There is another value called the average. It's not particularly important. It's a little bit lower than the RMS, and the average value is 0.636 of the peak. But you won't have to be too concerned with that one. This is the one you need to know, the RMS value. So if you multiply the peak value, if you want the RMS value, and you have the peak value, the RMS value equals the peak multiplied by 0.707, or if you want to do a rule of thumb, 7/10. So 7/10 of the peak value is the RMS value. If you want to know the peak value and you're given the RMS value, the peak equals RMS multiplied by 1.414. Now 1.414 just happens to be the reciprocal of 0.707. If you divide 0.707 into 1, you'll get 1.414. It's worth also knowing that 1.414 is also the square root of 2. You need to know these, and you need to know how to convert from RMS to peak and peak to RMS. And don't forget why you're doing it. The reason why you're doing it is because the RMS value is the value of a sine wave that has the same heating effect or will do the same work as that amount of DC. Just as a matter of interest only, because you will not be assessed on this, if you were to feed 2 sine waves to an oscilloscope has a horizontal input and a vertical input, X and Y axes. Instead of one signal, a sine wave, if you put 2 sine waves into an oscilloscope, the two of them mix together to produce what's known as Lissajous patterns. And in the old days, this used to be a way of determining the frequency of a sine wave. If you had a sine wave generator which you could set to 100 megahertz and you had an unknown signal in the megahertz region that you wanted to know the frequency of, you could mix the two together and produce one of these patterns, and you would get a ratio of the known signal to the unknown signal. And one of the most famous ones is the ABC pattern. To produce the ABC pattern, you need to feed to an oscilloscope 2 sine waves with a ratio of 1 to 3. So if one was on 1 megahertz, the other sine wave would be on 3 megahertz, and you would get this pattern. And if they weren't exactly 1 to 3 ratio, this pattern would roll to the right or roll to the left, and that's the ABC symbol. That's where they got the logo from. Just thought I'd mention that. If you're interested in learning more about oscilloscopes, and you don't really have to for your assessment, so you can do it now or you can do it when you've finished this course and you've got more time. If you'd like to learn more about oscilloscopes, go to the Radio and Electronics School website, click on Supplementary, and scroll down till you see a file called the XYZ of oscilloscopes. There it is. Oscilloscopes, the XYZ of oscilloscopes, and just download the file there. And it's a Tektronix publication, who are oscilloscope manufacturers, and it's a very, very good tutorial on the use of oscilloscopes. If you have a sine wave and you want to make it bigger, you need to use an amplifier. If an amplifier is linear, then by rights, whatever you put into that amplifier should come out. The only difference will be that it's bigger, because linear amplifiers just amplify things without changing anything. So if I was to put 2 cycles of sine wave into this linear amplifier, I would expect out exactly what I put in, the only difference being the output would be larger than the input. This would be a higher voltage signal than the input signal. Unfortunately, there is no such thing as a linear amplifier that is perfectly linear. As a consequence, not only will the original signal be at the output of the amplifier, but multiples of the signal will also appear at the amplifier, at the output of the amplifier. These multiples of the input signal are unwanted, and they're called harmonics. The second harmonic of a 10 megahertz signal would be 20 megahertz. The third harmonic would be 30 megahertz. The fourth harmonic 40 megahertz, and theoretically so on forever. But after 3 or 4 harmonics, the levels of the harmonics are so weak that we don't really worry about them too much. So harmonics are multiples of the original signal appearing in the output of an amplifier. They're undesirable, they're unwanted, and we need to get rid of them in radio. There's no such thing as the first harmonic. The first harmonic is called the fundamental, and in this case the fundamental is 10 megahertz. The second harmonic would be 20 megahertz, the third harmonic 30, the fourth harmonic 40, and so on. Right, let's go through some of the assessment questions that you could be asked, or similar questions you could be asked on sine wave, wavelength and harmonics. I've also put the URL to the virtual oscilloscope on the document for you, so if you want to play with the virtual oscilloscope, you can go to that URL, copy and paste it into your browser from this document. Alright, let's do some trial exam questions. Question 4.1. The average voltage of a half cycle of sinusoidal signal is, and the average is not really that important to us in radio, but we need to be aware of it. The average value, not the RMS value, the average value is 0.6 of the peak value. So if the peak value was 100 volts, the average value would be 63.6 volts. Question 4.2. The RMS voltage of a pure sine wave is 0.707 times the peak value. Question 4.3. The wavelength of a signal is 10 meters. The wavelength of the second harmonic is, well, the second harmonic would be double the frequency. If you double the frequency, you halve the wavelength. So the wavelength of the second harmonic would be 5 meters. The formula for wavelength is lambda, Greek letter lambda is the symbol for wavelength, equals 300 million, which is the velocity of light, divided by the frequency. Now, that's a little bit cumbersome for us to use in radio because the 300,000 is the velocity of light in meters per second. If we put, and I'll write wavelength instead of lambda this time, if we want to use wavelength in megahertz, we can make the numerator of our equation 300 divided by f in megahertz. For example, if we wanted to know the wavelength of 30 megahertz, we would go, so we want to know the wavelength of a 30 megahertz sine wave, we would go wavelength equals 300 divided by 30 megahertz equals 10 meters. You need to remember this equation for wavelength. This is the one that I would remember, this one here. Wavelength equals 300 divided by frequency in megahertz. Very important for formula for radio amateurs. This is the formula you're going to be using when you're going to be designing and building antennas. Question 4.4. The meaning of the term harmonic is a frequency which is a whole number multiple of the transmitted frequency. Yep, that's it. So if the fundamental is 15 megahertz, then the second harmonic, there's no first harmonic, then the second harmonic is 30 megahertz. Fundamental 15 megahertz, second harmonic 30 megahertz, third harmonic 45 megahertz. Question 4.5. Waveforms A and B shown below are observed on an oscilloscope with an identical time base. That means that the trace on the oscilloscope is being drawn at the same speed. And they're asking you a question about frequency. Which one of these is the higher frequency? Well, this one has 1, 2, 3.5 cycles. This one has 1, 2, 3, 4.5 cycles for the same time base, for the same duration, length of time on the x-axis. So we'd have to say that B has a higher frequency than A. Question 4.6. A wavelength in free space of a radio signal with a frequency of 3 megahertz is, well, using our equation again, wavelength equals 300 divided by frequency in megahertz. The frequency in megahertz is 3, and that's going to equal 100 meters. So the answer is 100 meters. Not too hard, is it? The second harmonic of a signal transmitted on 3510 kilohertz occurs at, well, the second harmonic would be double that frequency, which would be 720 kilohertz. The third harmonic of 21.15 megahertz would be 3 times 21.15 megahertz, which would be 63.45 megahertz. Last one. Yep, that's the last one. Question 4.9. The wavelength of a signal is 15 meters. The wavelength of its second harmonic, well, if it's a second harmonic, the frequency is doubled, and so the wavelength is halved. So the original signal had a wavelength of 15 meters. If you double the frequency, you halve the wavelength to 7.5 meters. And there you go for the sine wave, wavelength and harmonics. Please be sure to do the drill on this and test yourself, see how you're going. I'll see you back at the next tutorial. Thank you very much for your attention. Cheers for now. This is Ron, VK2DQ.